Yeah, okay. Good.
Brilliant. Sorry for that.
No worries.
Just unsure whether... Yes, now you can see the map, huh? Okay.
Yes, I can. Yes.
So the wave approach applies in the entire plane. Now we have geometrical acoustics, which is limited to the right-hand side of the plane for any value of damping, and we will speak of ray tracing, radiosity, and then we have a subdomain, which is the domain of the statistical theories of acoustics, in which we can find Sabin's theory and statistical energy analysis. Why is it a subdomain? Just because for these statistical theories, we need the important assumption of diffuse field, the field for which the wave is entirely disorganized. So, for instance, let's start by the most common statistical theory of sound. I mean, Sabin's theory of reverberation. The assumptions required for that theory are a large number of modes, a large modal overlap, usually say above the so-called Schroeder's frequency, light absorption of sound by wall in order to ensure a large number of reflection of rays, and also complex geometry in order to ensure that any ray travel or passes through any point of the structure. This is what we call ergodic billiard. And under that conditions, we get a diffuse field. And so the Sabin's law, which is well known, which states that the decrease of sound is the same rate at any points of the room, and the famous Sabin's law, which states that the reversion time is simply proportional to the volume and inversely proportional to the absorption coefficient. So what are the main features of this simple statistical theory? We have a statistical description of sound in rooms, and the primary variable is energy. And then under that condition, we have an emerging law that is Sabin's law. But we have no local information. Now let's turn to the second statistical theory of sounds, I mean statistical energy analysis. So the assumptions are conservative and light coupling, random forces, large number of modes, and light damping for the same reasons, because we need that the field is diffused in all subsystems. So for instance, imagine we have this funny car which has a highly reverberant behavior, and so we subdivide the complex subsystem into substructures. We apply an energy balance to any subsystems, and then we have the famous coupling power proportionality equation, which states that the power exchange between any two subsystems is proportional to the difference of the modal energies. So, in summary, what are the main features? We again have statistical descriptions of sound and vibration now. The primary variable is always energy. We have a linear superposition principle, but again, we have no local information on the behavior of waves. Now let's turn to geometrical acoustics. So, of course, geometrical acoustics is very ancient and maybe goes back to the Greek time. And so in geometrical acoustics, usually we say that we have at least 2 or 3 types of ray: direct ray, reflected ray, refracted rays. And in 1960 or 58, if I well remember, Keller's proposed to generalize Fermat's principle, which states that the optical length of any ray is stationary under a constrained path, and so he discovered that it was possible to introduce diffracted rays, diffraction by waves. And that we did is, in a recent paper published last year in Wave Motion, we applied the generalized Fermat's principle. So to the structure sound interaction, and we have shown that it exists only 6 types of rays, of hybrid rays, that is structural to acoustical rays or conversely. So when we speak of geometrical acoustics, there is at least 3 numerical approaches to solve the geometrical acoustics equations. So the most common and the well-known is, of course, ray tracing, and it exists many variants of ray tracing: rays with phase, without phase, cone tracing, Gaussian beams, and so on. But the main features is that we have a local description. Again, we have a linear superposition. The primary variable is pressure, the field itself, or energy, depending on if we have neglected or not phase. The second numerical approach is the image source approach, and in some special cases it is possible to solve geometrical acoustics equations by these techniques. And again, the main features is that we have local description, linear superposition, and the primary variable is again pressure or energy. And the last numerical approaches, the one for which that we will develop later, is radiosity. So what is radiosity? In radiosity, we imagine that we have 2 mirrors in regard and that they exchange energy. And we define a view factor, with this view factor, exactly like in thermics, we can have an energy balance of the exchange energy between these 2 mirrors. And then we write an integral equation that I will detail later on. And the main features of this approach that we have local description, linear superposition, but the primary variable is only energy. And also, but the reflection is limited to the Lambertian reflection. That's important. So now let's turn to the radiative transfer equation. So the principle is that we have a source point denoted by S, we have a receiver point R, and we have a boundary. So the source points have a power that I note rho, and on the boundary I put a fictitious sources which power is denoted by sigma. And then we write that the energy density at any point R is given by the superposition of the direct field, that is the source rho, and the reflected field given by the fictitious sources sigma. And in all cases, the decrease of energy is like 1/r square, where r is the source receiver distance. This is for a 3D domain. So the problem is now how to determine the fictitious sources sigma. So for that, we applied an energy balance, exactly like in radiosity method. So let's consider 2 points, P and P prime, on the boundary. And we consider the point P. We try to write the energy balance at point P. At point P, we can say that the energy which is emitted in direction U, the power P reflected, is a reflection coefficient times the power which is incident from direction U prime. So writing that in detail, we get a functional equation for reflection. So where on the left-hand side of this equation, you can see the reflected power, which is sigma at point P in direction U, and cos theta is the emitting angle, equals the reflection coefficient times the incident power, which is given by all point P prime, but also the actual or the primary sources eventually located into say between the point P prime and P. So as we can note, this is a functional equation where sigma appears on the left-hand side, but also on the right-hand side. So this functional equation may be solved. So I will not detail this demonstration, but the fact is that the solution of this functional equation exactly gives the image source method. So for that, consider a source S0 and a perfect mirror. So the functional equation is this equation where delta is the delta Dirac equation. I can solve that. And as you can see, we get something like that. And finally, we get that the energy density at any point R is simply the superposition of the direct source from S0 to R and the source S1, which is exactly the mirror source. So that's interesting because, of course, this is well known that image source applies in geometrical acoustics, but it was not obvious that image source can give a solution to these functional equations. And this functional equation can also be solved analytically in a second interesting situation. I mean, the circular billiard. So for that circular billiard, so I will not give the detail of the proof, but get that the energy density at any point R, where R is the distance from the receiver's point from to the center of the circle, and so we obtain this elliptic function. And so this is a representation of the energy density into the circular billiard, where the source is exactly there. This is a small white point. And this is the ray tracing solution. So as you can see, rays turn around a circle. This is why we get a circular symmetry of the solution. And we can also see that both methods give very close results. Now, let's illustrate the difference between ray tracing and radiative transfer approach. On the left, we have a ray which is reflected between two boundaries. So the first ray has a power, say 1. After 1 reflection, the power is R. After 2 reflection, R square. And after 3rd reflection, R to the power 3, and so on. So when we want to calculate the energy inside the system, we have to calculate the sum of this series, and we get, of course, 1 over 1 minus R. Now, with the radiative transfer method, what we did is that we have a primary source, rho 1, and we put two secondary sources, sigma 1 and sigma 2. We write the functional equation where sigma 1 is simply R times sigma 2, because the power which is emitted in this direction is simply that coming from right to left times the reflection coefficient. But for sigma 2, we have R times 1 plus sigma 1. This is because we must take into account also the presence of the primary source. We can solve this linear equation, and after a few calculations, you can observe that we get exactly the same solution. So, in conclusion, the difference between ray tracing and radiative energy transfer is just a numerical difference because both methods in fact are the same theory. Now, radiosity. What is radiosity? Radiosity is a special case for which the fictitious sources emits power like Cousin's law or Flambert's. And though in that case, the functional equation may be integrated over all angles, and let's have a look just at the bottom of this slide. And so now we have sigma, which just depends on P, no longer on the direction, so which is equal to the reflection coefficient times the incoming power. And the incoming power comes from primary sources first and secondary sources, that is an integral sigma over all the boundary, and as you can see, we recognize there the view factor coefficient. So this is interesting because with this equation we can predict stationary waves, but we can also predict reverberation time, because as you can see we have time there, and so that's something which is not used in thermics, but which may be useful in acoustics. So I now come to the second part of my presentation, and in this second part I will show you some example of application. So first start with this factory. It's a room with some obstacle inside, and for that we have put two sources, the red point there and there. This is a top view of the factory with the obstacle there in white, and we have applied two methods. First, ray tracing with the software which has been developed by EDF, my former company, and a second software that I have developed and which is based on the solution of the radiosity equation. And so there on the left you can see the map of sound pressure level obtained by ray tracing, and on the right the map of sound pressure level obtained by the radiosity equation. And as you can see, both methods give similar results, and if we compare more deeply the sound pressure level along this black line, we obtain this difference, which is quite small. So in conclusion, ray tracing and radiosity give exactly the same results, but provided that in ray tracing we adopt a Lambertian reflection, Lambert's reflection. A second example, more interesting maybe, because it is related to structural system. So we have two plates, and in these two plates we have excited one of them with a force point, and so this is a simple situation for which we can solve exactly the governing equation, and we have compared the level obtained by solving the radiosity equation with that obtained by solving exactly the wave equation. So the wave equation, this is an evolution of the level at one point of a frequency, and so the disturbed black lines is given by the wave equation, while the smooth line is a solution of the radiosity equation. And as you can see, the radiosity equation cannot predict the fluctuations, rapid fluctuations of the reference calculation, and the reason is that in radiosity we have neglected interferences between waves, and so we are not able to predict a model behavior. And on the right, for the second point, and second conclusion is that certainly we can't predict the small fluctuations, but we have a global prediction of the mean level. By mean, I say averaging over a small frequency band. A second example, this is an experiment that we have done on this furnace structure, which is made of seven plates, and so we have excited the structure by this vibrator, and we have measured the vibrational level with some accelerometers. And so this is an example of the evolution of the vibration over frequency, and the disturbed black curve is again that given by the measure, while the smooth curve is that predicted by the radiosity equation. And here, more interesting, this is on the right hand side, and this is an evolution of the level over this broken line. And so we pass through three plates, And so, as you can see, when passing through the interface between two plates, we observed that we have a gap of energy. And so the level is well predicted of this gap, and also the global decreasing of the energy inside the system is well predicted. A third example on the plate. So this is a plate which is highly damped, and also we have two slits there in order to diffract rays. And what we can observe again is this is the frequency evolution of the vibration, and the smooth line is the solution of the radiosity equation. And now at the bottom you can see the evolution of the vibration all along this line. And we had two vibrators in that case. This is why we have these two maximum. The method also applies for sound radiation. So in case of sound vibration, imagine that we have a structure, a buffer, a source point, and a sound radiated into an acoustical medium. Then I do not develop exactly, but the idea is to put some acoustical sources on the surface of the plate, sigma, and to write a functional equation by again applying an energy balance, and then solving the functional equation, we have that. So this is the evolution of the acoustical energy along a line there. And as you can see, the red curve is the exact calculation given by a very fine solution of the wave equation, while the green curve is the solution of the functional equation. So again, the functional equation gives the global evolution of the acoustical level, but cannot predict the small details, the rapid fluctuations. And there, on the right side, you can see the maps of sound pressure level into the acoustical domain. So this is the structure, the buffer, and then the domain. On the top right-hand corner, this is the solution of the wave equation, so that I call the reference solution. While on the bottom right corner, this is the solution of the radiosity, the spectrum. Sorry, the functional equation. So there is two main strips of sound, which are emitted in an exact angle, which can predict by the ratio of the sound speed to the structural speed. And then we have a triangle for which, of course, these two gaps overlap, and in which the sound level is a little bit higher. It also applies for sound transmission. So in case of sound transmission, we have many phenomena. So the first is a non-resonant transmission. Imagine that a plane wave, arrives from the bottom of the plate. It passes through the plate. Of course, there is also a reflected ray, and incidentally, there is a wave into the structural, into the structure. But the fact is that the angle of the transmitted wave is exactly the angle of the incident wave. This is that we call non-resonant transmission. The second possibility is that it exists surface radiation. Imagine that you have a structural wave into the plate traveling from the left to right. Then two acoustical rays are emitted, one to the top and one to the bottom. But in that case, the angle is exactly the angle that I have shown to you in the previous slides, the radiated angles, which is predicted by the ratio of sound speed and structural speed. Now, a third phenomenon is that when a structural ray arrives to the end of the plate, of course, there is a reflection, but also a diffraction into the acoustics. So the diffracted rays are emitted in all directions, and it exists a diffraction coefficient, capital D. And then a last phenomenon is that when we have an acoustical ray impinging on the edge of a plate, then there is diffraction toward the structure itself. So, with all that phenomena, combining all that phenomena and introducing for all phenomena fictitious sources sigma and solving the functional equation which is related, we obtain that. So in gray, this is the structure. On left and right, you have the buffer. The sources is located below the structure, and we visualize the sound pressure level above the structure. So on the top, this is the reference calculation, and on the bottom you have the solution of the radiative transfer equation. And here this is a comparison below the critical frequency. So remember that below the critical frequency we don't have any surface radiation. So the only angle that appears is the angle, the incident angle, which is transmitted to the upper acoustical domain. Now, a same comparison, but above the critical frequency. Above the critical frequency, of course, we again observe the strip at minus 105 degrees, but we also have surface radiation, and this is why we obtain two new strips at 115 angles. And as you can see, the comparison between the exact calculation and the solution to the functional equation is quite good, except that we cannot, of course, predict the rapid fluctuation of the field. The method also applies for multiple diffraction. In the case of multiple diffraction, imagine the following situation for which the source point is S, and we have a receiver point R, and now we introduce two wedges at point P1 and P2, which diffract the rays. So the method consists in introducing two fictitious sources sigma 1 and sigma 2 at the wedges submit, and then we also have a diffraction coefficient which depends on the incident angle phi and the emission angle theta. And so the idea is to write the functional equation sigma 1 and sigma 2. For instance, let's have a look on the first one, sigma 1, so the power which is emitted by these fictitious sources is the power coming from S plus the power coming from sigma 2. So this is why this is the power coming from S and the power coming from sigma 2, and each time we have a diffraction coefficient capital D which appears. So we obtain a linear set of equations on sigma 1 that can be solved, of course, easily, and then the energy field inside the domain is obtained simply by superimposing the influence or the contribution of the primary source and the two contributions from the fictitious sources. So this is a small example, diffraction by building. We have four diffraction sources, a primary source S and a receiver point R. And at the bottom, you can see the maps. This is the map of sound pressure level obtained by the binary element method, that is solving the wave equation. And on the right, we have solved the functional equation. And as you can see, the results are very close, especially there. This is a comparison on this black solid line. So excepted some very special directions for which we know that the diffraction coefficient is divergent. So this is a classical phenomenon which is well known in the field of the geometrical theory of diffraction. And the last example is that the functional equation or radiosity method also applies for anisotropic propagation. So to prove that, we have taken this small example on a square plate of 2 meters. And you have there the characteristics. It's a composite plate, and we have, so the method consists in modifying the function capital G. That the influence from source to receiver now depends not only on the distance, the source receiver distance, but also on the direction of the ray. So this is the directivity diagram of the source for the orthotropic plate. As you can see, the directivity diagram is no longer circular, meaning that there is a preferential direction of emission. And then on these maps, you can see on the left the results of the reference calculation, and on the right the results of the radiosity method. So both methods give similar results. In the vicinity of the source, we recognize, of course, the directivity of the source itself, but near the corner we can see some deformation on the line that are due to the reflection of rays into the corners. And again, if the radiosity method gave a global results, or not global but a mean results, as you can see, we cannot predict, of course, the rapid fluctuation of the field. But it also applies for anisotropic materials. So we took the example of a composite material with 3 layers, which values are 60 degrees, 45 degrees, and 60 degrees. And now we have a more directional emission for the source point. And you can see the comparison between the 2 fields, which is more or less square now. And the conclusion is the same, that is, the radiosity equation give a correct solution to this problem, except that we cannot predict the rapid fluctuation of the field. So I arrived at the conclusion. So we have proposed functional equation which can be solved by view factor method. In the case of Lambert reflection, this is what we call radiosity, but the functional equation can also be solved by ray tracing technique or image source technique. That's interesting. I did not give the demonstration, but we published a paper on the fact that statistical energy analysis is the limit case, the case for which reverberation of rays is so high that we get diffuse field. And so in that case, the solution of the radiosity equation exactly gives the same result as statistical energy analysis. And the method applies in many cases. We can tackle the situation of reflection, transmission through plates, diffraction by obstacle, sound radiation, structural response, but also anisotropic material. And that's the end. Thank you for your attention.